elastic potential energy. So this is the potential energy of a compressed spring. It's elastic potential energy. Elastic. Does anyone not know what elastic means? Like your waistband, elastic, or your bra strap? Elastic.
It's stretchy.
Stretchy, right, okay. So a spring stores elastic potential energy, which it can then give back again. It's a special kind of potential energy, similar to chemical or gravitational. It's elastic potential energy. Now, when you are pushing that dart into the spring on your Nerf gun, when you start pushing it, is it a lot of force or a little bit of force? A little bit of force. But as you continue to push it, what happens to the amount of force you have to apply? It increases. So there's this pretty cool law called Hooke's law, probably named after a guy named Hooke. And it is the force equals negative kx. In other words, the more you push, the more force there is. The more you compress a spring, the more force you have to apply. A little compression requires a little force. A lot of compression requires a lot of force. I'll talk about that in a second. Yeah, talk about why that negative is there in a second. Yes? Yes. Because the F equals kx means a small compression, that's x, requires a small force. A large compression, big X, requires a big force.
I'm so big brain.
You're so big a brain. Just make sure that big a brain is functioning for at least the next 5 years. So, Rome asked, what's the deal with the negative in front? Anyone have any idea why Hooke's law has a negative in front?
Is that because the force of the spring is pushing the opposite direction that you're pushing it?
Exactly. That's exactly right. So it's kind of like a normal force. If you are pushing the spring this direction, you are applying a displacement that way, but the spring is pushing back with a force that way. I exaggerated the arrows so you could see them. But when you are pushing on the spring pushes back, creating a normal force, if you will, that is negative. Does that make sense? Now the magnitude is important, where you usually push with the same force against Hooke's law. So if the spring is pushing back with 4 newtons, you're pushing forward with 4 newtons. Make sense?
Yes.
Okay. Now we know that work is force times distance, right? And we also know that work is the change in potential energy, right? So could you plug in Hooke's law for force and get how much potential energy you add to the spring?
Yeah, you did Hooke's law and you multiply that by the distance, right?
So work, what would work equal? Negative kx times displacement. Negative kx times displacement. Now the cool thing is, what's the unit of displacement? What is the unit of displacement?
Meters.
Meters. Guess what the unit of compression is?
Not meters.
Meters.
Oh.
So what you get is this handy little formula when you multiply those two things together, and you get that equals that. So the energy stored in the spring is 1/2 kx squared. 1/2 kx squared. So the kx squared is hopefully obvious. We'll talk about where the 1/2 comes from in a second. Oh, it's down there, the little graphic.
So this
It will, yeah. Because when you pull the trigger and the dart launches off, it releases that stored potential energy in the form of kinetic energy. Yeah.
Why would you square and 1/2 of
wouldn't you just have it by D?
Because meters times meters is square meters. So x is meters, d is meters, so you get kx squared. Okay. So it's work equals kx squared. Now, why is the 1/2 there? When you start compression, the force is very, very small.
Yeah.
When you end your compression, the force is larger. So what we want is the average force you're applying.
So it's the 1/2.
That's the 1/2. Okay. Basically, the 1/2 is basically saying the force you start applying plus the force you end up applying divided by 2. It's the average. The 1/2 tells you it's an average force. It basically keeps us from having to do calculus. So instead of having to say delta, dx PD over d 1/2 k dx, we just say.
That's nice. To explain
Yeah.
1/2.
I'm sorry, what?
So to explain 1/2.
Yeah. So explain 1/2 is you start pushing with very small force, you end pushing with a lot of force, and the area under the curve is the work you do. So 1/2 is this plus this divided by 1/2 is the average force. So you're using the average force. If you want to do, if you knew how to do calculus in areas under the curve, you would just do a k to force, or a force to x graph. That's the area of the curve, which we're not going to do because you don't have to do calculus. But does that make sense why the 1/2 is there? You're starting with very little force, you're ending with a lot of force, so the 1/2 basically tells you the average. All right, so if this makes sense to you, how much would a spring with a constant of 200 compress if a 2 kilogram mass is dropped onto it from 1 meter above? Boing. So you take your 2 kilogram mass, which is right here, from 1 meter above, and you drop it on your foot, or you drop it on a spring. So how much will that spring compress? I gotta have a calculator.
Drop this in 1 year.
No, I thought.
So I did this on
Compression.
Yes, x is compression.
How much would it be?
with that potential energy. So it's 1 meter above. P is 1 meter.
I will have to say.
Force times.
You need to see,
What's the force? The force is 20 newtons. Times 1, which would be 20.
Does that make sense? Potential energy grab equals potential energy spring.
Don't we need PE?
So,
Yeah.
what would x equal though? That would be the.
That's what you're solving for.
Okay.
That is the spring compression.
That's so long.
So whatever potential energy the block has, you're going to drop it. It's going to go boing, 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 boing. It's going to stop moving. When it stops moving, all the potential energy the block previously had is now stored in the spring.
So the original potential energy would be.
Aha, I was right.
1 meter above and 20. So it's
Wait, why does potential energy equal to thing? Oh wait, no, that is, never mind, sorry.
So
I got my formulas mixed up for a second.
And
happens to the best of us.
times 10 times 1 is going to be 20. And we're 2 times.
What? So,
20, so the potential energy is 20.
what is the
Wow.
Yeah. What are you trying to say?
The formula is 1/2 kx squared.
I don't know if that's a change.
You don't have that, you're trying to find it.
You're solving for x squared.
Yeah.
So you need potential energy as
Is
GA,
20, yeah.
and then you're solving for x squared.
Yeah.
What if
right? No, it wouldn't be negative. It's only,
Oh, 20 over 100.
oh my god, it's
Well, yeah. Springs, I mean, the spring is like, it's not a huge spring, it's a spring. By the way, a spring constant of 200 is the kind of spring you would find in like a chair. You know, like one of those like that kind of chair, or that, wherever the black one is. That's about a spring of 200. The springs you find in the car are in thousands, and the spring you have in your ballpoint pen and your clip pencil are like 0.1, 0.01.
X would be
X would be in meters, yes.
Oh.
So, I think I got it.
Is it a tiny number?
It is.
How tiny?
It goes to 10, 10. So that's one place.
No. No? Okay, so this is 20 equals 100x squared,
Go round up.
Yeah.
square root of 0.2. So what is square root of 0.2? 0.44 meters?
It's
0.447.
0.45?
That's if you round.
0.45 meters?
Yeah, which is what we do.
Well, that's not what
Okay. Does this make sense what we just did?
Yeah.
We took a whole bunch of potential energy, we first converted to kinetic, and then that kinetic turned into potential energy in the spring. All the stored potential energy that was dropped got compressed into the spring, and we just said mgh equal to 1/2 kx squared. Cool? And how about this one? I turned the image on its side, and what if the same block struck the spring horizontally? We're going to assume there's no friction in the horizontal direction. What if the same block struck the spring horizontally but traveling 3 meters? Then how much would the string compress? Yep, now it's kinetic energy. Same block traveling 3 meters per second strikes the same spring, but now it's traveling horizontally.
So wouldn't
Yeah. So whatever block, whatever kinetic energy the block is carrying as it's traveling, gets absorbed into the spring to compress the spring.
Oh, this is gonna be even smaller.
Oh yeah, I got such a small kinetic energy.
Yeah.
Yeah.
It's okay, things can be small, it's alright.
Wait,
It's not about the size, it's important, it's about how you use it.
It's not gonna be that much smaller though, right?
Not that much smaller?
Still
Okay.
have to constant.
You can just keep telling yourself that.
9 equals 1/2.
I bet constant.
Right, he says.
The constant's the same, yeah, it's the exact same
Talking about
spring.
the answer.
The constant's the same, it's the same spring.
Alright.
Scott's back there falling asleep. He's like, no, I was dreaming, I was thinking about screens. Like, what would
That would be a
happen?
scary dream.
What would happen if you had this brain? Alright, so kinetic energy is 1/2 mv squared, and spring potential energy is 1/2 kx squared. So can we just throw out the 1/2s? And just say we have a mass of 4 and a velocity of 3 squared equals spring of 200 and then x squared.
It's a massive two.
Mass of 2. Thank you. Mass of 2. Yeah. Mass of 2.
And time.
So this is 18 over 200 square root. Square root of 18 over 200.
0.09 equals.
0.09? Oh no.
Or
Okay.
that's
Equals
what
x
x squared.
The square root of 0.09,
Yeah.
That's
which is 0.3 meters? Yeah. Sounds about right. That makes sense? Yeah, honestly though, if this made sense to you and you got this, give me a thumbs up. If you want to talk about it some more, wave your hand around. Okay. So the great thing is energy is energy is energy. Now if we have friction, then we have to talk about loss of energy to heat. Well, we don't care about that today. Yeah.
Are we gonna have to put this all together after these first?
Yes.
By the end of this class.
Not the other class, no. But no, but in the simulations in the labs, you will have to say, oh, I lost this much to friction. But the good news is you're not going to have to do more than say, I lost this much to friction. Because to basically have a force and a distance and a mu and all that, that requires calculus because your force of friction changes with velocity, the square root of velocity, so we're just not going to believe that. We'll say, I lost this much to friction. That's all we care about. Ending point, starting point. Okay, there are two types of collisions. When things collide, in fact, there's a whole unit just on collisions. There are two types of collisions. One type of collision is one where all the energy is stored in the systems stays in the systems. Okay. In other words, the energy is going to be conserved. When energy is conserved, we call it an elastic collision. All the kinetic and potential and elastic energy that is in the system to begin with stays in the system. It's an elastic collision. Conservation of energy. And again, we're going to mostly spend most of our time with collisions in our momentum unit, which I believe is the next unit after this one. But yeah, so in an elastic collision, you don't lose any energy. All the energy that's in the system to begin with stays in the system. The kinetic energy of block 1, the kinetic energy of block 2 is the same. Total energy is the same before and after collisions. And like these two blocks or balls, one comes to rest, so it has no kinetic energy to begin with, and then it has a bunch of kinetic energy. The green ball has kinetic energy, and then it gives all that energy to the blue ball, and then it has no kinetic energy. That's an elastic collision. Pool balls are very close to elastic collisions. Very close. Not exactly. Because they still can make a clack, and they still warm up the felt as they travel across.
Is there a loss of energy due to sound too? Or no? Okay.
Because sound is just the pushing away of air molecules. So what you're really doing is you're pushing the ball. If in real life, a green ball would hit the blue ball, plus push a bunch of little balls called air molecules away too.
Okay.
So it's not just hitting the green ball, it's also hitting a bunch of air
And
molecules.
it's also, is that like under air resistance too? Or no?
Kind of, yeah.
Okay.
Yeah.
Say you got like the inclined plane, would you have to take into account if you also heard a noise when it hits the ball?
Uh-huh. Yeah. The good news is it's very, very small. And practically speaking, when you're dealing with a 1 kilogram cart over a couple meters distance, the actual amount of clunk as it hits is very small. But just understand that elastic collisions are what we use to make the math work. Okay? If you remember your chemistry, we talked about perfectly ideal gases and then real gases.
Yeah.
And we use perfectly ideal gases to make the math work. In reality, that's not really what happens. So same thing with collisions. We use elastic collisions to make the math work. In reality, they don't exist in our realm, at the macro scale.
It's like a percent field.
Kind of. The good news is, if like our cars are so low in friction that we can basically say, we can ignore friction because it's just it's a rounding error.
So it's like theory kind of?
It just makes the math work. It allows us to ignore enough of the things that you can do the math at the junior high school level
Okay.
or the senior high school level. So if a elastic collision conserves energy in the system, what do we call it when you lose energy? Inelastic. You call it inelastic. Okay, inelastic. So in reality, elastic collisions don't exist because there's always air molecules vibrating. There's friction and stuff. So yeah.
Did you get an elastic collision in space or
No, because even in space where there's no air molecules around it, the molecule itself will vibrate, and that vibration creates heat.
Okay.
Kind of like when you hit somebody, their muscles compress, your arms compress, and your tendons and everything get warm.
no? Yeah.
Okay. Like if I gave you this little bottle of BBs, you could shake it and 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 shake it, and even though they're not changing, you'd be like, hey, they got warm. They got warm because the molecules vibrated inside.
Okay.
So pretty much the only place you see any elastic collision is at the quantum scale with atoms. In fact, that's actually important. I think that's a test question. The only place you see a perfectly elastic system is at the atomic level.
Atomic level.
Yeah.
So you can't create a situation
Where there's an elastic collision?
Yeah.
No.
Whether they even
Only at the atomic level. Because you ignore things so you make the math work. So you'll do elastic collisions throughout your junior and senior year in high school, and then you'll learn calculus And then if you have a really, really sadistic professor, he'll make you do inelastic collisions in college.
What a lit guy.
Quantum
I know.
realm or quantum?
Maybe it's a dude, maybe it's a chick. It could be a dude, maybe a chick. But
I'm not judging.
I'm not judging. Yeah.
Loki. Nah.
My favorite professors at college were women. Interesting. Anyway, power. So power is the rate at which work is done. Power is the rate at which work is done. It is simply W over T. And again, we're going to look at the beginning and the ending such circumstance. We're not going to do calculus. We're not going to look at the power curve. Computers can calculate power curves. We're just going to look at the beginning work and the ending work, divide by the average time, and call that average power. Okay. The unit of power is the watt. Unit of power is the watt. And a watt is a joule per second. Now, a joule per second is such a small number. What you frequently see is kilowatts. In fact, in Europe and Asia, they don't use horsepower. They don't say, this engine has 200 horsepower. They say, this engine has 35 kilowatts. They're like, wow, that's a lot of watts.
Yeah, horsepower sounds way cooler, so. Probably why it's American.
Yeah, it's Americans. And fun fact, actually, I'm going to back up before we let you write what you need to write down before we talk about power companies. Now, this is going to be something I'm going to plant a seed and not talk that much about it until we get to electronics. When we get to electronics, we'll talk about how much it costs to run your Xbox for an hour. But understand, if you ever looked at a power bill, you don't actually buy power from a power company. You actually buy energy. Because the unit that you buy is called a kilowatt hour. 1 kilowatt hour. In Henderson, my kilowatt hours cost me 11 cents. It's about what they cost here too. So for 11 cents, you get 1 kilowatt hour.
How much is a kilowatt, like, relatively?